So we've gone through a couple lectures on this topic now, and it is how it's basically related to a detailed transport model for liquid permeation through membranes. And I use the example of desalination or reverse osmosis as a base case for this, but the same analysis applies to other situations that are now becoming of increasing interest in the membrane field. One of them being organic solvent nanofiltration, where instead of distilling, say, mixtures of benzene and cyclohexane in order to separate them, you can put them in contact with a solvent-resistant membrane and use pressure-driven transport in order to bring about that separation. And thereby you avoid the phase change and the energy penalty associated with that you normally find in distillation. And so this is an area where there have been a number of startups formed. I don't believe there are any commercial products out yet. But the analysis of those types of problems follows exactly on from the water and salt transport that we've seen. And this problem is remarkably intellectually rich relative to the final result. So if you apply a hydrostatic pressure difference across a membrane, the final result is actually quite similar. In many polymer materials, as you ramp this pressure difference, the flux of liquid through the membrane just goes directly proportionally with it. The details of how you get from Fick's law to this final form, as we've seen in the last couple of lectures, does involve a number of steps. And what I have walked you through has been one of the turning points in the membrane field. And that is that in the very early days, 60s and early 70s, there was a notion that, absent any other possibility, that if you applied a pressure difference across a material and had flow of small molecules through it, that the only way that could happen is if that material were somehow porous. And so there was the rise of a theory for reverse osmosis, or in general liquid transport through what I would call non-porous membranes, that was based on the principle that there must be pores in the material that would allow flow driven in the same way that pressure drives flow through a pipe. And so using laws like the Hagen-Poiseuille law were used to describe flow through membranes. Now, this supposed that there were pores in the material, but they were just so small that they couldn't be seen. And 40 years ago, that view took hold in the literature, and today there are still a few pore flow people around. Hard to believe in negotiations. But you will see it rise up from time to time in the literature. And this problem was ultimately resolved by one of our faculty members here, Don Paul, really put the nail in the coffin of the pore flow people with this basic chemical engineering analysis of how a pressure gradient induces a concentration gradient inside the material and ultimately flow. If you read the literature today, you will often find that we're very nice to one another. That wasn't always the case, and there were bitter back and forth over this particular concept between the pore flow people and the solution diffusion people. Ultimately, the solution diffusion concept was the much more widely accepted version of the solution to this problem, and it brings about a concept that I wanted to introduce to you as we get towards the end of the semester, called Occam's razor. And how many of you have heard of this? What does it mean?
You pick this if like you're given different kind of like explanations for something, the one that's most true is probably the simplest.
Yeah, so that's a philosophical position. not a scientific guarantee. But the pore flow model required that there be physics available, that is, the presence of these pores that could not be detected by any microscopy or spectroscopy or any available technology. It required the presence of pores as an additional assumption to arrive basically at this equation. The solution diffusion model doesn't require that assumption. It assumes that the materials are non-porous and that the way that water, salt, organics, other small molecules partition and transport through polymers is according to the laws of thermodynamics for the partitioning, and then laws of Fick's law of diffusion for transport, and that same framework or physical picture governs not only water transport and ion transport through these types of materials, but also governs liquid transport through other types of polymeric materials, gas transport through polymers. Any sort of non-porous material can be, the transport properties can be described within the framework of the solution diffusion model. And so that is ultimately what has taken hold and provides a unifying concept within this field. If you look back now at the beginning of the semester, I gave you some excerpts from a paper by Sir Thomas Graham from the mid-1800s. And he was studying the transport of gases through natural rubber, and was actually the first person to formulate the solution diffusion model, the idea that the penetrants dissolved in the polymer and then were transported. At that time, Fick's laws had not been widely developed, but was transported by some molecular mechanism through the material. And so we come forward now 150 years, and these same concepts are the underpinnings of the field for all kinds of applications: controlled drug delivery, gas separation, barrier packaging, and other types of membrane applications. And so the basic question that we asked as part of this analysis was, how does a hydrostatic pressure difference across the membrane cause a transport first of water, but really of any liquid? And we brought into evidence work in the literature that showed conclusively that as you increase the feed pressure across a membrane, you don't do much to the concentration of water that's dissolved in the upstream phase, but you do lower the concentration of water at the downstream phase. And that is a consequence of this pressure discontinuity at the backside of the membrane, that as the feed pressure increases, the chemical potential of water at the backside of the membrane increases, and in order to make it equal to the chemical potential of the low pressure water on the permeate side of the membrane, some water has to desorb from the membrane. And that creates the concentration gradient that then drives the flow by ordinary Fickian diffusion through these materials. Now, getting to that point through the thermodynamic analysis requires a number of steps, but what we ultimately came up to was that for pure water or pure solvent transport through the polymer, the thermodynamic activity of water on the feed side was essentially equal to 1. It doesn't change with pressure, and that the water or solvent activity on the downstream side of the membrane depended on the exponential of the molar volume of water times the difference between the feed and permeate pressure. And so as you increase the feed pressure, you lower the water activity at the downstream side of the membrane, and you therefore lower the concentration of water, because the activity, although it's not necessarily a linear function of concentration, using something like the Flory-Huggins model, activity and concentration go the same direction in this case. And this also led to the concept that has now been observed in organic solvent nanofiltration, and that is the concept of a limiting flux in these materials. The lowest value that the concentration of penetrant in the polymer can take at the downstream side is 0. You can't have concentrations lower than that. And so that provides a maximum driving force and therefore a maximum or limiting flux. And this is not observed in the case of water because the molar volume and partial molar volume of water in these materials is of the order of 18 cc's per mole, and at pressures that we could normally access for things like desalination, you just never can drive with any sort of reasonable feed pressure. You can never drive this concentration to zero. This is not true with organic, large organic molecules that permeate through polymers. There, the partial molar volume can be in the hundreds of cc's per mole, and it doesn't take much in the way of feed pressure to actually dry out the backside of the membrane. And you see these flux versus delta P curves that are initially linear but then level off. You see those in the work of Paul and Ever Lima that I discussed discussed in the last lecture. And we were then wrapping this up to understand the effect of the presence of a solute in the solvent or the water on either side of the membrane, what that would do to this analysis. And we use the analysis of putting salt in water, because in a desalination application, we would be using this phenomena in order to separate water. It goes back to a concept that you probably learned in high school, if not before, of osmosis. If you have a membrane that's largely permeable to water but not salt, and you separate a salt water from a freshwater solution, there's a tendency for the fresh water to dilute the salt water. The water concentration gradient is in this direction from right to left, and so the natural driving force for water transport is across the membrane. This is the phenomenon of osmosis that underpins life in many cases. And so that flow of water can induce a difference in level in this device, which induces a hydrostatic pressure on the saltwater side that's higher than the freshwater side. And when that pressure is equal to the so-called osmotic pressure, the net rate of transport of water across this membrane is equal to zero, because as we've seen, the presence of a hydrostatic pressure gradient across the membrane can also set up a flow of water from the saltwater side to the freshwater side. And when that hydrostatic pressure is equal to the so-called osmotic pressure, which is a measure of the activity of water in the saltwater side, then the net flow across the membrane is zero. If you apply a hydrostatic pressure greater than the osmotic pressure, then flow of water can be driven against its concentration gradient, and this is the realm of reverse osmosis that I talked about in this slide. It's also coherent with the results of the experiment that Abbé and Nollet ran. One can make this experimental measurement of the osmotic pressure or the thermodynamic activity of water in a solution with a very simple device that has a membrane that's permeable to the water or solvent, in the case of an organic solvent, but not to the solute. And as a result of that, the solvent will diffuse into this chamber, raise the height of liquid above that of the pure solvent, and this height is related directly to the osmotic pressure, because this just by the density of the solution times G times H is the hydrostatic pressure that's raised, and once the hydrostatic pressure is equal to the osmotic pressure, then there's no further increase in this level. So you can read off directly the osmotic pressure in an experiment like this. I showed you a table of typical osmotic pressure values. So your the blood circulating in your body has a variety of species in it, including ions, and the osmotic pressure of your blood is about 8 bar, just in case that's of interest to you. And the types of applications we're interested in for desalination, low concentration salt water would be just a few bar, and seawater has an osmotic pressure of upwards of 23 bar. And what that means is in order to purify water by desalination, you always have to have a feed pressure that's higher than the osmotic pressure. That's the point where you start to drive pure water against its concentration gradient across the membrane. And this is the energy, the cost that you have to put into the process in order to perform the separation. And so desalination of seawater is typically carried out at pressures that are higher than about 30 bars, so to have some driving force. I thought we would just walk briefly through the thermodynamic analysis of what the presence of a solute in a solvent does to the chemical potential of the solvent, because in the case of water transport out of a saltwater mixture, water would be the solvent. In the case of an organic mixture, these expressions can be extended to multiple solvents. And so, if we look back at this device and ask what is the condition for chemical equilibrium for the solvent in the solution and in the pure solvent, the solvent chemical potential depends upon the solvent concentration and on the hydrostatic pressure relative to a pressure reference pressure is shown here. This is just a standard expression for chemical potential of a solvent at a mole fraction in a solution of X1 and a hydrostatic pressure P. The reference state is taken to be that of pure solvent with a mole fraction of 1 and a reference pressure of P0. For us, that reference pressure is typically going to be atmospheric or whatever the permeate pressure is in a given experiment. The solvent activity in turn is related to the mole fraction of the solvent in the solution. And for the simplest case, for an ideal solution, the thermodynamic activity of the solvent is just linearly proportional to the mole fraction of that solvent. This would be for an ideal liquid solution, and this result comes directly out of basic statistical mechanics, where you would consider the entropy change of mixing of a solvent with a solute, where the mixing is random and there's no interaction between the solvent and solute. It leads directly to this result. And if the solution is non-ideal, then there is an activity coefficient term that has to be added and accounted for. But we'll consider in this case the ideal solution case for now. So in the pure solvent phase, which we'll call alpha, the chemical potential of pure solvent can be written this way. The log of the activity of pure solvent is 1 relative to the reference state, which is that of pure solvent. And in the pure solvent phase, we assume that this is also at the reference pressure. If you think back to this experiment, the pure solvent in an osmometer would be at atmospheric pressure, and so that would typically be taken as the reference pressure. In the solution phase, which we'll call beta, the chemical potential of the solvent is written as the reference chemical potential plus RT times the log of the activity of solvent in that phase, which we're going to approximate by the ideal solution model, and then a term that involves the partial molar volume of the solvent in the solution, and an integral over the pressure difference from P0 to P0 plus the osmotic pressure, because the hydrostatic pressure in this case at equilibrium will be equal to the osmotic pressure. And so if we equate the chemical potential in the pure solvent and solution phases, we get ultimately to this expression. Typically at the ranges of pressures where these osmotic experiments are done, the partial molar volume of the solvent is essentially constant, and it's often about equal to the molar volume of the solvent. And so we can bring the partial molar volume outside the integral and integrate it to get the expression that's shown here. And what this shows, if you rearrange it just a bit, remember that this is the thermodynamic activity term. We've written it for an ideal solution, but in fact this result is general. And if the solution is non-ideal, then there'll be an activity coefficient here in front of the solvent concentration in the solution. And that activity coefficient can be calculated by a variety of solution phase thermodynamic models. And what it shows is that the osmotic pressure of a solution is a direct measure of the thermodynamic activity of the solvent in that solution. For dilute solutions, in all of the cases that we would be considering that would involve, for example, salt desalination applications, at least the standard applications that would be things like brackish water and seawater desalination, the concentration of salt is quite low, and so we can write this logarithmic term as shown here and approximate it by the first term in the Taylor series expansion to get the expression at the bottom of the page. Again, this shows that the osmotic pressure is a direct measure of the solvent activity in the solution. The solute mole fraction is the number of moles of solute in the solution divided by the total number of moles of solute and solvent, which is water in our case. And if the solution is ideal, then the total number of moles of material in that solution is about equal to the number of moles of solvent. The partial molar volume is, to a good approximation, the total volume of the solution divided by the moles of solvent. And so we can rewrite this expression as shown here. And this is the osmotic pressure of an ideal solution. And it is a direct analogy to the ideal gas equation. So this is the equivalent expression for ideal solution, where the hydrostatic pressure in the ideal gas case is replaced by the osmotic pressure. And this is the number of moles of solute. So for an ideal gas, PV is equal to nRT, and for an ideal solution, pi V is equal to nRT. If that solution is non-ideal, as in the case of an ideal gas, there would be a thermodynamic activity correction factor here. Just one other bit of history about this. So it was Van Hoff who originally developed this, this concept of osmotic pressure of ideal solution. And he did that as history would have it, in conjunction with one of his buddies and a discussion they had where he was noting that another fellow was measuring the effective temperature on osmotic pressure and found that for every degree rise in the temperature, the osmotic pressure went up by about a factor of 1/270. So now you think about that. If the temperature is around ambient, right, it's 298, 300, close to 270. And so if you raise the temperature by a degree, then the osmotic pressure would go up by some factor that would be proportional to that. And this is reputed to be the idea that led Van Hoff to develop the theory of ideal solutions for thermodynamics. And you can read a little bit more about that in this historical article by Ed Mason. This is osmotic pressure is one of the colligative properties, which is a property of a solution that depends on the number of solute molecules, but not their chemical nature. Again, in the ideal solution world, there are no enthalpic interactions between the solvent and solute, and each of the particles or molecules in the solution is taken as a point particle. Other colligative properties other than osmotic pressure are freezing point depression, boiling point elevation, and vapor pressure depression of a solvent by a solute. And sometimes these methods are used to make measurements of osmotic pressure because they all are interrelated to this concept of the effect of a diluent, if you will, or a contaminant on the thermodynamic activity of the solvent. I just provided for reference the osmotic pressure coefficient for a solute dissolved in an organic solvent in terms of the millimeters of solvent. That is, this would be here's the osmotic pressure. This would be the height of the benzene that you would measure in that osmometer, and how that changes with the molecular weight of the solutes. You can see that small molecular weight solutes give rise to much larger effects of concentration on osmotic pressure than large molecular weights do, simply because the higher molecular weight at a given concentration and mass concentration, you have far fewer molecules. And you can see the comparison for the freezing point depression, boiling point elevation, and vapor pressure depression. All of these results can be derived in a similar fashion from the thermodynamics of ideal solution. So if we come back to the problem that we were looking at before, what does the effect of salt do to water transport and then ultimately salt transport through these membranes? We come back to the picture that we had before. We now modify that to take account of the fact that in the solvent phases on either side of the membrane, this will not be pure solvent anymore. And I've been showing throughout this a slightly anatomically incorrect picture of the concentration profiles, showing that the concentration of water in the feed was slightly lower than that in the permeate. That picture is now correct when there is a solute in the feed, and that solute concentration is higher on the feed side than in the permeate side. The concentration of solvent as a result will be lower on the feed side than on the permeate side, and it is as a result of this pressure gradient that you actually can drive the solvent essentially uphill in terms of its concentration gradient to get a net flow of material across the membrane. The way we modify the expression for, we start from exactly the same point, that the chemical potential of the solvent in the feed is exactly equal to its value in the membrane at the upstream or feed side of the membrane. And we now take account of the fact that the feed is no longer pure solvent. It has a certain concentration in it. And the way concentration affects chemical potential is always through a thermodynamic activity term. And that activity term can in turn be related to the concentration of solvent in the feed. In the case of a simple ideal solution, this will just be related to the osmotic pressure of the feed, as we saw a couple of slides ago. We also we can equate the chemical potential of water in the feed with that write it for that in the membrane, and it introduces it's exactly the same form that we had earlier when we just had pure water permeating across this membrane. We equate those two chemical potentials at the feed interface for the solvent. The result is shown here. Insert the definition of osmotic pressure for the activity of solvent in the feed, and we get ultimately to the expression that's shown here at the bottom of the page. And this is exactly the expression that we had for pure solvent or pure water transport across this membrane. The only difference is we're now accounting for the effect of solute concentration on the thermodynamic activity of water in terms of the osmotic pressure. And you can see that that is an effect that lowers the thermodynamic activity of water in the solution and therefore in the membrane. And again, here's the ideal solution case that would relate the thermodynamic, the osmotic pressure directly back to the concentration of the solute or salt in the feed. We come to the downstream side and again use exactly the same analysis that we used before, equating the chemical potential of the membrane in the downstream side to that in the membrane at the downstream side to that of the chemical potential of the solvent in the external solution. The expressions are written in exactly the same way as we did for the feed side. We again wind up with a term that in the permeate stream, if it's not pure solvent but has a concentration of solute in it, it will introduce a term that is has the activity of the solvent in the permeate side, and this can again be written in terms of the osmotic pressure of that solution in the permeate side. And so the final expression we have for the activity of the solvent in the membrane at the permeate side looks exactly like the one we used before, except it has a term in it that now accounts for the effect of solute concentration on the thermodynamic activity of the solvent in the membrane. And again, this is a negative effect in the sense that the higher the solute concentration is in the permeate solution, the higher is the osmotic pressure, the lower is the thermodynamic activity of water in the external solution and therefore in the membrane. And so These are the final expressions for the activity of the solvent and the permeate and the feed. We'll need those in just a moment in order to link the concentration gradient inside the membrane to the concentration of solvent and solute in the external solutions. We started this discussion with a very simple version of Fick's law that doesn't include any of the possibility for convective effects or so-called frame of reference corrections for transport. And if you integrate that across the membrane with a constant water diffusion coefficient, you can write the expression for the flux as shown here. Now, we had also studied this problem following the analysis of Hall and Eberlima, and they account for the effect of so-called convective effects or frame of reference effects on the solvent flux. These effects are typically unimportant when the solvent concentration in the membrane is below 10 or 20%. Nevertheless, we can start from this analysis and in the general sense write Fick's law, including these frame of reference effects as shown here. That expression can be integrated to get the flux of solvent in terms of the concentration difference inside the membrane. L is the thickness of the membrane under actual use conditions, and as I mentioned last time, under cases particularly for organic solvents when at high pressure, the concentration gradient across the membrane can be extremely high, and so the concentration of solvent is much lower at the downstream side, and this can actually dry out the membrane to a certain extent and shrink it, decrease its thickness. And so we have to be able to relate the actual thickness of the membrane under use conditions to its thickness under dry conditions, because that's what we can measure experimentally, and we take the result directly from the Hall and Eberlima analysis for that to get the final expression for the solvent flux through this membrane in terms of the diffusion coefficient, molar volume of the solvent, concentration difference of solvent inside the membrane, and the dry membrane thickness. We'll use the analysis that we just did a moment ago to relate the concentration of solvent inside the membrane to the thermodynamic activity in the external solutions. First, we'll recast the result for flux in the form that's shown here. It turns out that it's a little more convenient to deal with this ratio of concentrations of solvent in the membrane at the permeate relative to the feed side than it is to deal with it in this form. I'll show you that here in just a moment. We combine the flux model with now our expression for the thermodynamic activity of the solvent in the permeate and feed solutions. We can write what we're headed for is to relate this term to the activity, thermodynamic activity terms, and ultimately to the terms that are over here, because it's the pressure differences and the osmotic pressure of the solute concentrations in the solutions that one can actually measure. And so we'll first take these results and cast them into the ratio of the thermodynamic activity of the solvent in the membrane at the permeate side divided by that at the feed side. And the result is shown here. And you can start to see how this is going to work out because you start to see the emergence of that term. Remember that the water flux is proportional to delta P minus delta pi. Well, here it comes. This is coming directly out of an analysis of the thermodynamic partitioning of the solvent into the membrane at these two points. If we use something like the Flory-Huggins model for these thermodynamic activities of solvent, we could write that in the nomenclature we're using as shown here, where pi is the Flory-Huggins interaction parameter, and you can start to see now the emergence, the correspondence between this ratio of thermodynamic activities and the ratio of concentrations of the solvent in the membrane at the feed and permeate conditions. And again, what we're after here is to be able to relate experimentally measured variables like the pressure and concentration of solute in the external solutions, to a concentration gradient in the solvent in the membrane that we really can't measure. And it is that concentration gradient that is driving the transport of solvent through the membrane. And so we have to be able to relate the internal concentration gradient with the external measurable parameters, and we do that through this thermodynamic analysis. We can write this ratio of thermodynamic activities also as shown earlier in terms of delta P minus delta pi. And it turns out that in the case of, particularly for water transport through membranes under desalination conditions, that even at very high feed pressures, the difference in the concentration of water in the feed side of the membrane and the permeate side of the membrane is actually very small. And as a result of that, if the concentration of water on the feed side of the membrane is a little bit lower, but not too much lower than that on the permeate side, this term in the numerator and this one in the denominator are essentially equal to one another, and they cancel out. And that turns out you can run this, you can calculate the value of this term for a range of chi values and also a range of water uptakes that go all the way up to something like 50%. And this term will be within 1% of 1 for any pressure range and concentration range that we would need. And so we can write this ratio of concentrations of water inside the membrane as shown here. And now this is a key result that we need because it relates the internal concentration gradient in the membrane to externally measurable quantities that we can actually go into the lab and measure. And so we can put that into the expression for the flux and get the result that is shown here. It turns out for systems like, and what you'll see is that for like organic solvent transport through polymers with very high values of partial molar volumes, the flux can indeed be a nonlinear function of the driving force. For something like water transport in the desalination membrane, the value of the partial molar volume is so low that this term can be approximated by the first term in the Taylor series expansion, and that will lead directly to this form. You can start to see now how we're getting this back to the equation that was determined empirically as a performance equation for desalination membranes, that the water flux was directly proportional to the difference in delta P minus delta pi. Just a couple more steps here, I promise. We can write the ratio of the concentration of water in the membrane on the feed side to the concentration of water in the external solution on the feed side as a partition coefficient. This is a standard definition of a partition coefficient, concentration of a species in one phase relative to its concentration in another phase, and that introduces a familiar looking term, right? D times K. What would this be? That would be permeability. Right? So this is how permeability gets introduced into this equation. Now, it turns out that at least for situations involving water and salt, the concentration of water in the feed will be 1 gram per cc. The specific volume will be 1 cc per gram, and so this term often is essentially offsetting. If we define water permeability as the water diffusion coefficient times its partition coefficient, then we write this in terms of the water flux as shown here. And in many cases for desalination membranes, the water content is not extremely high, and so this term is often negligible relative to 1, and the final expression would just have the water permeability divided by the dry thickness times this grouping of terms, which represents the driving force for transport. This is essentially the concentration difference of water in the membrane at the feed side minus that at the permeate side, expressed in variables that can actually be experimentally measured. And so that's the final expression for water transport. And I'll have just a short section on the effect of salt on that. If I can get back to so this was our starting point, and we've now derived from first principles the expression for the relationship between water flux and delta P minus delta pi. You can take the expression on the last page and it will tell you directly what this parameter A is in terms of the molecular properties of the material. That is the water diffusion coefficient and partition coefficient or water uptake, and the thickness of the membrane. The last one is just to relate the salt flux to the concentration difference in salt, and that turns out to be rather straightforward. So this is showing the direct connection between our flux result and the performance equation that's typically used in the literature under the condition where this term, with water uptake level being low, this term is essentially negligible relative to 1. And this is the relationship between the so-called A parameter that's widely reported in desalination literature and the water permeability and membrane thickness. And you'll note that this looks quite a bit like the expression you would find if you had gas flux through a membrane written in terms of a permeability coefficient per unit thickness times the pressure difference across. And that's not an accident. These are both examples of the application of solution diffusion model to transport in this material. The salt transport is given by a very simple expression involving Fick's law. That is that the salt flux at steady state depends on the concentration gradient of salt in the membrane and the diffusion coefficient of salt in the membrane. For these pressure-driven separations where there's no electric potential involved, if you take salt, for example, sodium chloride and water, the ions will be dissociated. And in order for the solution to remain electrically neutral, every time a sodium ion transports through this membrane, a chloride has to come with it. There is no alternative to that. And I showed you several lectures ago how this so-called salt diffusion coefficient is related to the diffusion coefficients of the cations and anions. It turns out that electrostatic coupling in the ion transport allows one to write this relationship, the salt diffusion coefficient, in terms of diffusion coefficients of the individual ions. The basic picture here is that the ions migrate according to diffusion independently, but then the electrostatic coupling between them links them, so we can actually talk about diffusion of salt rather than diffusion of individual ions, although at steady state for a monovalent ion, the flux of sodium and the flux of chloride have to be equal to one another, otherwise the solution is not going to be, we can't maintain electrical neutrality in the system. And so we can very simply integrate this result to get the final result for salt flux and in relation to the change in concentration of salt in the external solutions. We've related the concentration of salt in the membrane to that in the external solution with a salt partition coefficient, and typically at the levels of salt that are in desalination membranes, one could take the salt partition coefficient to be about the same at the feed and permeate interfaces, and that's what's been done to get this final version of the expression. And we can see then that the empirical performance equation for how salt flux depends on salt concentration is simply related to the salt permeability, which in turn is the product of the salt partition coefficient times salt diffusion, and the thickness. This will, like the water case, will be the dry thickness of the membrane effectively. We typically write the performance of a desalination membrane in terms of two parameters. One is flux, solvent flux, and the other is rejection of the solute, or rejection of salt. Rejection is defined as the difference between the salt concentration in the feed and the permeate relative to the salt concentration in the feed. This is an operational definition that is easily measurable in the laboratory. If we use the transport parameters defined earlier, we can relate this rejection back to the fundamental transport properties, water and salt permeability, and the driving force for transport across the membrane, or ultimately to these A and B values that are widely reported in the literature. It's very common in this field to report the performance of these membranes not in terms of permeabilities of the water and salt or water and solute, but in terms of rejection. And this is partially a result of the fact that in modern desalination membranes, the effective membrane thickness is extraordinarily small. It's on the order of less than 100 nanometers, as thin as 50 nanometers, and so the thickness is hard to measure, which makes it hard to get at the detail values of these individual permeability coefficients. But one thing that should always be kept in mind is that rejection is not an intrinsic property of a material. It depends upon material properties through these permeability coefficients, but it also depends upon operating parameters. And I often see confusion in the literature about mistaking rejection values as a direct measure of the performance of the material, when in fact one should be talking about this in terms of permeabilities. Now, this is all I have on this particular topic, and I think I'm going to wind up early today because I don't want to start the next section before I've had a chance to rework some of the notes, because I'm going to change a bit of the end presentation in the course, because we've already talked about some of the ion transport that I wanted to get at earlier. So I'm going to let you guys go a bit early today, and hope that you'll use this time in contemplative meditation about transport phenomena in polymers.